Hello, my name is Dr. Johnson. I'm one of the AP Stats teachers at Capella High School. I welcome you to this presentation on graphical presentations of data. I'm going to begin by distinguishing different types of variables. We will today talk about categorical variables and quantitative variables. Quantitative variables are subdivided into discrete and continuous. A categorical variable takes on values that are category names or group labels. The graphs of categorical data show the frequencies or relative frequencies that observations fall into each category. Can you give me examples of categorical variables? Yes, gender, race, age group, that is, are you young or old, political affiliation, highest degree earned. These are examples. What's wrong with this analysis? This is a study of different ethnic groups in Chicago, in a Chicago retirement community, and I have 4 categories labeled 1, 2, 3, and 4. What's wrong with this analysis? Well, what's wrong is that they went ahead and calculated the mean. And it doesn't make sense to calculate the mean for categorical data. I could easily renumber the categories with different numbers and get a different mean. So it just doesn't make sense to perform functions like averaging with categorical data. Quantitative variables. A quantitative variable is one that takes on numerical values for a measured or counted quantity. It does make sense to average these values. And there are again 2 types, discrete and continuous. Can you name any numerical variables? Here's a few. Age, height, GPA, population, income, mass, time, rate, volume, density, anything you can measure really. Categorical versus quantitative variables. Do we ever use numbers to describe the values of a categorical variable? Well, yes. Not every variable that takes on a numerical value is quantitative. For example, phone area codes. It doesn't make sense to average phone area codes or take the standard deviation of phone area codes. Do we ever divide the distribution of a quantitative variable into categories? Sure. Sometimes we put numerical data into categories such as age categories. A discrete variable can take on a countable number of values, usually the counts of items such as soccer scores, test scores, number of children. But we are able to count the number of possible values. A continuous variable can take on infinitely many values, and usually this is the measurement of something, such as there are an infinite number of possible heights for students in our classroom. Other examples, the distance a person can throw a baseball, or every possible x value where x is between 0 and 1. These are continuous variables. Let's identify the following variables. Color of cars in the parking lot. Is that categorical or quantitative? It's categorical. The number of desks in a classroom. Is that categorical or quantitative? Well, that's quantitative, but then is it discrete or continuous? It's a discrete quantitative variable. We can count the number of desks. Zip codes. Is that categorical or quantitative? That's categorical. Zip codes represent a place. So the fact that Capella has a zip code of 75019 and Plano has a zip code of 75075 doesn't mean that Carrollton has the average of those two zip codes. It doesn't make sense to average zip codes. The amount of time it takes employees to drive to work, well, that is continuous and quantitative. Now I want to talk about different ways of graphing categorical data. Here I show two ways, the pie chart and the bar graph. Pie charts are good because they can emphasize each category's relationship to the whole. I've drawn a pie chart on the right there, and you can see that I've labeled each of the categories and I've given the percentage for each of the categories. Whenever you draw a pie chart, remember to label the each of the categories and tell me the percentage. Bar graphs make comparisons across categories easy. So on the right there I have a bar graph, and it makes comparisons across categories easy. I can easily see that there were more hazel eyes than green eyes. With pie charts, you have to make sure that the numbers, the percentages in the pie add up to 100%. Pie charts are not good when there's a large number of groups. Here's a pie chart of the call center calls by hour. When two variables are categorical, the raw data can be summarized in a two-way table that gives counts of observations for each combination of values of the two categorical variables. So let's talk about two-way tables. Here's a two-way table classifying 178 high school students by gender and whether they pierce their ears. So I have two variables, gender and whether they pierce their ears. Gender is represented by the two columns, and pierced ears are represented by two of the rows here. 178 total high school students. From this table, we can ask you lots of questions. We can ask you, what is the if I chose a student at random, what is the probability that the student is male and has pierced ears? Or what is the probability that the student is male? Or the probability that the student has pierced ears? Or that the student is a male or has pierced ears? These are favorite questions in AP Stats. Now, often we take those two-way tables with counts and we convert them to percentages. So in my previous graph I had 178 high school students. Now we calculate their percentages and represent it out of 100%. So the percent of males with pierced ears is 19 out of 178, or 10.7%. The proportions in the interior are called joint relative frequencies of the two categorical variables. So I have the joint relative frequencies highlighted in red. Those are joint relative frequencies. When you want to examine one of our categorical variables by itself, we look at the marginal relative frequencies. Marginal relative frequencies. These are the row and column totals for a two-way table. So I can ask you, well, what is the marginal relative frequency of being female? And you'd say 49.4%. Marginal relative frequencies are the row and column totals. Conditional relative frequencies. A conditional relative frequency is the relative frequency for a specific row or column of the contingency table. And there are separate conditional distributions for each value of the variable. So, what is the distribution of piercing based on the condition that the person is female? So assuming that the person is female, what is the distribution of piercing? Well, now we're going to look at the column for female only. That is the conditional, these are the conditional relative frequencies. Let's talk a little bit more about bar graphs. Here's a bar graph of pet owners in the Orange County, and you can see we had many dog owners and fewer cat owners. A couple comments here. Notice that with bar graphs, the bars do not touch. The bars do not touch. Also, it doesn't make sense to describe the shape of a bar graph. I mean, you're not going to say that this is, skewed to the right, because the order of those columns is arbitrary. I could change the colors, the order of those columns, and I'd get a different shape. So it just doesn't make sense to discuss the shape of a bar graph. Graphs of categorical data. So I'm going to show you a few more graphs, but I'm going to use this data. Yellowstone National Park staff surveyed a random sample of 1,526 winter visitors in the park. They asked each person whether he or she belonged to an environmental club. The respondents were also asked whether they owned, rented, or had never used a snowmobile. Here's the two-way table summarizing the results. So you can see, first of all, that there were a lot more people that had never joined an environmental club than those who had. So that's the first observation I see. And for each person, they were also asked whether they never used a snowmobile, they had been a snowmobile renter or a snowmobile owner. Here, I created a side-by-side bar graph for this data. A side-by-side bar graph displays the distribution of a categorical variable for each value of another categorical variable. The bars are grouped together based on the values of one of the categorical variables and placed side by side. So I group all of the bars for the people who responded no to environmental club membership together, and I group together all of the bars that for the respondents who said yes. These are side-by-side bar graphs. A segmented bar graph. A segmented bar graph. A segmented bar graph or a stacked bar graph displays the distribution of a categorical variable as segments of a rectangle, with the area of each segment proportional to the percent of individuals in the corresponding category. So if I go back here to this graph, notice on the left-hand column I have percent. If I were to take the three columns on the left-hand side, these are the columns for respondents who said no. If I take the green, the red, and the blue columns for the no people, and I stack them one on top of the other, I would get the no column in the segmented bar graph. Likewise, and I did the same thing for the environmental club memberships for people who said yes. Notice with the right-hand side, we've got a large number of people who said yes, and of the large number of people who said yes, most of them had never used a snowmobile. So my column on the left is where I stack all of those, and you can see most of it is blue on the right. Relative frequencies must add up to 100%. So if you are asked to draw a segmented bar graph, make sure that both columns add up to 100%. A lot of students get that wrong. When you are asked to draw segmented bar graphs, make sure both columns add up to 100%. Now let's talk about association, and this is a favorite topic for questions on the AP exam. We say there is an association between two variables if knowing the value of one variable helps predict the value of the other. If there is no association between the variables, one would expect that the heights of the segments to be about the same for each category. So suppose that I asked a group of students at Capel High School what their favorite breakfast cereal is. And I categorized the students by male or female. And for the male and for the female, I made stacked bar graphs, and the height of each of the boxes in this stacked bar graph represents the relative size of that serial. And I did the same for students at New Tech. That's on the right-hand side. I've got the results of a poll of students at New Tech. So the question is there an association between favorite breakfast cereal and gender? Well, let's look at the Capel High School data first. If I told you that I randomly selected a female, would that help you identify, excuse me, let me rephrase that question. If I told you that I randomly select a student and their favorite cereal was the gray cereal, would that help you predict whether I had selected a male or female? Not really. Not really. So with the data from Capel High School, we're going to say that there is no association. Knowing the value for one variable doesn't help you predict the value of the other. Now let's look over here at New Tech. Here I have quite different results. If I told you that I randomly selected a student and their favorite cereal was the gray cereal, would that help you predict whether the student is male or female? Well, yeah. You'd say if the student is most likely a male. What if I told you that I randomly selected a student and the student was a female? Would that help you predict what their favorite cereal is? Yeah, you're likely to say that the student might have the blue cereal as their favorite. So we say that the data for Capel High School is not associated because these two stacked bar graphs look pretty similar. Whereas the data for New Tech, there is an association between these two variables because there's some significant differences in the heights of each of these blocks in the columns. Association. You will be required to know this. This is a favorite topic, so make sure you understand the concept of association between two variables. Mosaic plots. This is new to the AP curriculum. On this graph, or on this slide, I talk about how to create a mosaic plot, but rather than go through it, I'm going to show you graphically. So, on the top here, I have my side-by-side bar graphs and my stacked bar graphs. Notice that the segmented bar graphs, or the segmented bar graphs, can be obtained by stacking the bars in the side-by-side bar graph. So you can get graph B by stacking the bars in graph A. Now, the mosaic plot is the plot that's on the bottom there. In the mosaic plot, the bar widths in the mosaic plot are proportional to the number of survey respondents who are environmental club members and who are not environmental club members. So remember, we had most of the respondents were not environmental club members and fewer were. So the column for the not is much larger. That is a mosaic plot. Suppose that I have I took a poll and I got some female respondents and some male respondents. I've classified my respondents by gender, and then I further classified them by whether they consider their body image to be underweight, overweight, or about right. As you can see from this mosaic plot, I had more female respondents than male respondents. My question is there an association between these two variables for the 1,000, for the respondents in this sample? Yes, there is an association between perceived body image and gender. That's the conclusion, but then you have to explain why. Males are about 4 times as likely as females to perceive that they are underweight. Males are about 4 times as likely as females to perceive that they are underweight. Notice that the green bar, the green box for males is much wider, or is much taller than the green box for females. Males are also less likely to perceive that they are overweight. The blue box is a little bit shorter for males and females. However, the overwhelming majority of both genders perceive that their body image is about right. So, yes, there is an association for those 2 reasons, but overwhelmingly, majority of both genders perceive that their body image is about right. I wanted to just describe briefly some things that you want to avoid when drawing graphs. Here's one. The area of a graph should correspond to the magnitude of the value it represents. So here we have we have the DirecTV trying to promote its product, saying that there are 95% of your favorite channels are on HDTV compared to dish and cable, but the problem is here that the column width is much different, and so that tends to overemphasize DirecTV's value. And you want to avoid exaggeration in graphing. This graph, the line at the back represents 18 miles per gallon in 1978. That's a line that's only 0.06 inches long. And the line that's closest to us is that this line represents 27.5 miles per gallon in 1985. That line is 5.3 inches long. So this is a gross exaggeration. That's your presentation for today. Thank you very much.